Hello everyone. So we will wait for 5 more minutes so that everyone can join and then start. Okay. So meanwhile, we are waiting for others to join. If you have any questions from the previous session, you can ask, or from like anything that was taught in week 1 and week 2 in the course. So if you have any questions, you can ask now. Anybody? Any questions? I'm audible, right? You can also post your like question in the chat box and also tell like if I'm audible. Okay. My screen is visible, right? Anyone? Okay. So maybe I can start. So if you have any questions, ask me now or like by the end or like in between also you can ask your questions. So what I'll do today is first of all I'll just briefly recap whatever we have done in the previous session and then start with this session. So I'll uh, tell you the concepts and also ask you some questions related to those concepts, and you can answer in the chat box or you can unmute yourself and answer, and then I'll tell you how to solve these type of questions. Okay, so let's start. So first of all I'll introduce myself. So I am Akansha and I am a PhD scholar at University of Queensland and IIT Delhi, and this is the second practice session of geographic information systems, and like it will be more useful if you guys go through week 1 and week 2, like you go through the week lectures and then come to the sessions, because then like you can ask some questions also if you have any doubts from those uh, lectures. Okay, so I'll start. So first of all, we studied. So the topic is geographic information system. So geographic information is kind of information about the location and what is existing there. And there are some key technologies related to it. So first is global positioning system, which kind of all of us know, because like in our mobile phones also we have this GPS system. So this is basically used to track the location of like anything like uh, your location or anywhere, like there are like bunch of satellites which are kind of tracking everything, positioning everything. So this technology is called as global positioning system. So we will study this later in more detail. The next one is remote sensing. So remote sensing is basically sensing things from a distance. So in this technology, what we do, we like get information from satellites or any other remote sensor, like without going to the location we can get information about that particular place. And geographic information system is basically uh, related to like how you use the data of like any location. Uh, So that is what geographic information system is. And like in like geographic information system, what we do, we extract information of the real world and then make like different layers of GIS world. So this is real world, this is GIS world. So in GIS world, what we do, like real world is very complex, but we want to see the pattern of a like specific property like topography or soil properties. So what you want, you are only, if you are only interested in soil properties, you will extract information about soil properties from different like surveys or from satellite images like from remote sensing, and then you can map that as a layer in this real world. So this is like for soils, this is for topography. So what we are doing, we are making this real world uh, like converting this real world in a simple layer, so that we can extract maximum information as per our like aim. Okay, so this is what we do in geographic information system. So you can see there are different spatial data layers like soil, location, land use, land properties, villages. So there are lots of things that are there, and these layers are very useful in extracting the information that we are interested in. Okay. So now we also studied about the types of data. So there are spatial data. So that refers to locations like addresses, coordinates, and the other one is attribute data. So this is basically uh, giving you the descriptive information about what is there in that location, like properties, land use, rainfall data, elevation data. So whatever descriptive information that we have about the location is called as attribute data. Okay. Now the other thing is relationship and indexing. So we need to like have some relationship or indexing in between the spatial data and attribute data. So that linking is called as relationship or indexing. Okay. So this also we will understand through different questions I'll be giving you, and then through that we can understand what this basically means. This is basically linking the spatial data to attribute data, like how are you joining these two data. Okay. Now, importance of GIS. I think in the last class we studied about the importance of GIS. So there are like lots of things, lots of real world phenomena that we can understand by making GIS layers. Like you can look at the rainfall pattern, how it is changing, whether a location is getting more wetter through time or more drier through time. You can do this by making a GIS layer, and that can like help in decision making, policy making, and lots of other things. So this is quite interesting and very important today. Okay, so also in the last class we studied about the different data models that we have. So first is raster data and the other one is vector data. So in raster data we have regular grids or cells, and this one is called as like smallest unit is called as pixel, and each pixel has one value associated with it. So that is why this can be very useful if like if your data is continuous. So at if at every location you need to have a value, then you need to make a raster model. Okay, so each grid will be having one value. So you can map elevation, rainfall, soil properties, like lots of things you can map. Land use, land cover, you can map in a raster model. Okay, so we also talked about different properties like smallest unit, how much space the smallest unit is encoding is called as resolution, and the locations that are kind of similar characteristic, we can convert them into a zone, and each pixel will be having one value. Okay, and location is like what lat long value it is occupying in a real world. So what is the location for which it is having the data. So ordered pair of coordinates are required, and then pixel values is basically this is a digital number which spans from 0 to 255 for a 8-bit image. So this also we understood what is pixel value. So this basically depends on the intensity of light that is going to the detector from that particular area. Okay, so till now any doubts? Anyone? If you have any doubts, you can ask. Okay, so we'll move on. The next model is vector model. So vector model is basically it can represent points, lines and areas. So suppose you want to show cities or some archaeological sites, then you need point layers. If you want to show uh, rivers or uh, railway tracks or road networks, then you need a line layer. And if you are showing a country or a state, then you need like polygon layer. Okay, so this is what vector model is, and this is kind of like not continuous, like it will not represent a continuous data. This will represent a discrete data. Okay. Also in the last class, I told you how can you download the data. So like if you like if somebody is new, you can watch the previous session recording. But the thing with previous session recording is it was zoomed in, so it's not that like clear. But still, like if you have any doubts while downloading the data, you can ask me. I can show you. Okay. So you can go to this website and then you can download different data sets. You can also download digital elevation data. You can also download Landsat data. So there are lots of data sets that you can download from this website. Okay. So, and soon we will start working with like data, and we'll be using QGIS. and ArcGIS also. So QGIS is open source, so you can download and use it. And then we will be using like some data sets download after downloading from these sites. So you can have some hands-on uh, practice also. So that is why it is like important for you to know how to download the data. It's like quite simple. So you can try and downloading it, and if there is any problem, just ask me, okay? So now in the last class, I was thinking if the digital number that pixel value starting from 0 to 255, if that was clear or not. So that is why I'm giving you this slide. So if you take any image, Landsat image or any raster data, and if you zoom in, you will see it will look something like this. Okay, so any digital image that you have will look something like this. So it will be having like these like gray small pixels, and each pixel will be having some uh, intensity or digital number associated with it. Okay, so I'll show you like tell you what is the difference between a photographic film and digital image. So a photographic film, what happens, your there are some silver iodide that is there, and when the photons hit these silver iodide grains, they change color. So it is basically a chemical reaction that is happening, and because of this you will get a photograph. So it will depend on the number of photons, and it is very localized. So like the reaction will happen wherever the photon is getting hit and what is the intensity of photon. So this is what happens in photographic film. But in digital image, what happens based on your pixel, um, how many pixels are there, the area is divided into like different uh, squares, you can see, and these smallest units are called as pixels. And at each pixel, like these detector that is corresponding to that pixel, there are some photons that are going there. So suppose here the you can see here the intensity of photons, like this is very high, so that is why this is very bright. Wherever the intensity of photon is less, the gray value is going to be less. So if the number of photons are very less, such that the detector cannot detect it, then what will happen? You will get a digital number of 0. So it will be like completely black pixel. If number of photons is very large amount, then your value will go to a maximum value. Like for 8-bit image, it will be 255. Okay, so it will be very bright, and in between are going to be shade of gray. Okay, so this is what digital number means, and this depends on the intensity of signal received by the sensor. Okay, so you can see like we will open an image, and if you zoom in, it will look something like this. And at each like pixel, there is one value that correspond to digital number, and it depends on the intensity of signal. Okay, so I hope this is clear. Any doubts, anyone? Okay, so if no doubts, we can move to the next part. So I was also talking about resolution of images, right? So resolution can be of different types, but the resolution that we were talking about was spatial resolution. Okay, so I'll use a pen. Okay, so suppose you have one image, and in the image, the smallest pixel correspond to an area in the real world. Okay, So if the spatial resolution is 30 meter, then that means the smallest pixel, this one, is representing 30 by 30 meter of area on land. So this is going to be 30 by 30 meters. So I don't know if I can write. So it will be 30 by 30 meters. Okay. So this particular pixel here, this one, sorry. So this particular pixel, the smallest unit, is representing 30 by 30 meters on land. Suppose this particular image is 1 by 1 meter, like pixel value is 1 meter. So that means it will represent 1 by 1 meter on land. So this is going to give you more information as compared to this one. So suppose you have something that is like smaller than, so suppose there is one small pond or one small like park or something, anything that is like having dimension less than 30 meters, then it cannot be like well represented in this one, but in this 1 by 1 meter it will be well represented. Okay, so you can see here we have like more spatial information as compared to this one. So this is what spatial resolution means. And if you are doing any analysis, so you should know like what spatial resolution do you need. Okay, so what is the thing that you are trying to see? What is the dimension of that particular like the smallest uh, area that you want to see, and then you can uh, take the satellite data or choose the satellite data which is like kind of in line with your analysis. Okay, so this is why it is important for us to understand the spatial resolution. Okay, next one is temporal resolution. So temporal resolution is basically dependent on the revisit time. So suppose there is a satellite which will come like every year to a particular area. Okay, so for every year it is like moving, and every year it is coming to Delhi or crossing Delhi, and like at every year we have one image. And suppose there is one satellite which is like kind of very fast, and it will revolve and come to Delhi daily on daily basis. Okay, and suppose you have a situation of like you have an assignment of disaster management. So for disaster management you have to act very fast, like how the situation is changing you need to know that very frequently. So you will not take any satellite data that is having like resolution in years, like only one data point within a year. So you will not get any information about that particular disaster. But you, if you have a satellite data which has like resolution to, it is like revisiting the area daily, then you can monitor the disaster situation for that particular area. Okay, so this is why temporal resolution is important. So I hope this is clear. Anyone? Any doubts? No doubts? Okay, so we'll move on to the third type of resolution, which is radiometric resolution. So radiometric resolution is dependent on the gray values that we have. So you can think of them as like different colors. So suppose you have a drawing and you only have like 2-bit means 4 colors. So you can make like your uh, you can fill only 4 colors in that drawing. But if you have 8-bit, that means you have 256 values, different values, so 256 different colors. So you can fill in that like image using 256 different values, DN values, digital number values. So this is going to give you more information about the uh, reflection or intensity change uh, given by the photons. Okay, so more information about how much reflective this is as compared to this. But here you don't have much information. Here we have lots of information about the reflectivity of different areas. Okay, so this is what radiometric resolution is. So this is related to the DN values. So if it is 2-bit image, you only have 4 DN values, but if it is 8-bit image, you will have 256 DN values. Okay, so this is radiometric resolution. Now the fourth is spectral resolution. So you know we have light and in electromagnetic spectrum you can like have different wavelengths of light, and you can divide the different wavelengths into different bins. So suppose you are dividing the visible light into three bands: blue, green and red, and these are like 120 nanometer bins. So the width is 120 nanometer. And suppose, so what you will have for each area, you will have three values: one for blue, one for green, and one for red wavelength. But if you divide into like 9 bands, then you will be having 9 values for each location. So this is having like more information about wavelength as compared to this one. Okay, so more information in different wavelength ranges as compared to this one. So this is what spectral resolution is. So for high spectral resolution, you need to have more number of bands. Okay. So I hope this is clear. Any doubts, anyone? So I hope not. So we'll move on. So the next part is metadata. So we talked about this. So whenever you are downloading the metadata, you need to know like which satellite was used to collect the data, what was the time when this data was collected, how it was collected, what are like different what is the projection system or reference system, what processing has been done. So these kind of information about the data is called as metadata. Okay, so in the last class we also looked at how can we kind of check the metadata of the data that we are downloading from the USGS website, right? So that we have checked. So every time you are downloading the data, also check the metadata and make a document of the metadata. Okay, it is going to be very useful. Okay, so now in the last class I told you about the QGIS software. So QGIS is something that you can download. So this is the link through which you can download. So I have already downloaded it. So I'll just open it. So while it is opening, anybody tried to download QGIS? Anyone? So you can see we have like this interface of QGIS. So here we will add the maps. Here we will like all the layers that are here is going to be shown here. This is like main menu. Then we can also have a toolbox. So while doing the analysis, I'll add the toolbox also. Okay, so we can use this QGIS for different kinds of processing that we are going to learn. So today maybe I'll tell you how to digitize any image and uh, how can you like uh, georeference any image layer that you have. Okay, so we will be doing that in QGIS, and ArcGIS I don't have. Okay, so somebody asked a question. So the thing is like both are having like all the tools are same, but for ArcGIS you need to have like it is depending on you like which one are you comfortable with. Okay, so if you are using ArcGIS, you are going to be more comfortable with ArcGIS. Same with QGIS. If somebody uses QGIS from the beginning, they are going to be comfortable with QGIS. But the thing is, QGIS is kind of open software, so you don't need any license to download or use it. Okay, so I think like QGIS, from QGIS you can also like directly download SRTM data, and there are because it is open source like there are lots of perks. So I recommend if somebody is starting using any ArcGIS or QGIS, so they should go with QGIS because like if even if you change your institute, like once you change your institute, your license is going to expire for ArcGIS. But if you are using QGIS, it like you don't need any institute or license, so it's better if somebody is starting. So what I'll do, I'll teach all the methods that we will do in both QGIS and ArcGIS. But so right now, like this laptop is new, so I have not downloaded uh, ArcGIS in this one yet. So today I'll only be using QGIS, but I'll like uh, tell all the steps in both ArcGIS or QGIS. Okay. So it basically depends on you. Like if you are comfortable with ArcGIS, you can like use that one also. But it is not very difficult to switch from ArcGIS to QGIS. Okay, so now the next question is, when you are doing any analysis in GIS, ArcGIS, QGIS, you need to have like all the layers in the same projection system. Okay, so why this projection system is important, we are going to see first. Okay, so let's start. Uh, what is coordinate system? And coordinate basically like it will give you the location like where are you on the earth. So you need what latitude values and longitude values. Okay, so latitude values are basically latitudes are basically these lines which these circular lines on the globe. So these are imaginary lines. There are no real lines on the earth, but for our like uh, reference or our interest, we have made these lines so that we can understand what location somebody is referring to. Okay, so these are latitudes and these parallel lines are called as longitudes. Okay, so I hope my cursor is visible, right? So if you see in the coordinate system, we need to know some terms So the great circle is like the intersection of the plane of the earth. So, and there is a line of longitude or meridian. So this is prime meridian and all other lines. So the prime meridian is one which passes through Greenwich, England. So here it passes through the England. So that is why this is like this is kind of defined as prime meridian. And so this is 0 degree. And if you go here, you will go to 10 degree east, and if you go this, then it will be 10 degree west. So these are like reference point. This is reference point for longitude, and for latitudes, the equator is 0 degree. So that is like the line that is like kind of cutting our globe in half. So that is equator, and this is 0 degree latitude. And then once you go up, it is 0 degree north, 10 degree north, 20 north, and once you go down, it will be 10 degrees south, 20 degrees south. So this coordinate system, I think everybody knows what is latitude, longitude. So these are basically designed for us to understand, uh, like if somebody says a 0 degree, um, uh, 0 degree latitude, so you know, like we are talking about equator. So this is kind of given by us so that we can understand which location we are talking about. Okay. Now, so this is what I was talking about. So prime meridian is 0 degree longitude, and from here the reference is set, and other meridians are like compared with this one, and these parallels, so equatorial, and then if you go up, it is north, down, south. Okay, so now for defining any coordinate system, you will define a latitude and a longitude. So this latitude and longitude, you know how it is defined. So the reference for longitude is prime meridian, and the reference for latitude is equator. Now, what happens? We need to, like, we have a 3D system. Our Earth is 3D, and when we make maps, it is a 2D system. Okay, so we cannot, like, it for mapping a 3D Earth to a 2D map, we need to have like some projection, like how are you projecting this 3D map into 2D map. So that is what is called as projection. Okay, and there are like graticules. So these are basically terms. So graticules means lines of parallel and meridian. So these lines are called as graticules, and grid is basically like uniformly spaced straight line. So these basically are given in the map so that we can like have the reference like which uh, latitude or longitude this particular location is there. So while we do georeferencing, if we have these sets of grids, then it is very easy for us to georeference, or easy for us to know the exact coordinate of a particular location. Okay. Now, as I was talking about this, the projection is basically done because we are representing a 3D world in a 2D map. Okay, so there are different ways you can map it, and that uh, representation, 2D representation of 3D space is called as projection. Okay, so now you can see uh, uh, projection is 2D representation of 3D map. So suppose we are using this kind of system. So here what is happening? Basically like most of the maps that you come across, they use this cylindrical projection system. So here what is happening, each circular region, so each what you can call parallel, each parallel are represented like this. So this particular one, 60 degree, is represented here. This is 30 degree, and then this is equator. So these are kind of cylindrically projected. But here what is happening, you are like the area, actual area of this, um like uh, this area that we have from 60 degree to uh, like poles, north pole, this area is kind of expanded in this kind of projection system. You can see this area is very small compared to this one, but still in this kind of map it is having like it is occupying larger area as compared to what is actually there. So whenever you see a map, cylindrical map, and you can think like this Greenland is very large, but it is actually not large area wise. It is basically because of the projection that we are using. Okay, so because of this kind of projection, this Greenland area is coming out to be very large, but it is not that large. Okay, so this, whenever you see a map, you should think like it is only a representation of our 3D world. Okay, so this area is kind of distorted when we do this kind of projection. Okay, so let's see. So this is Mercator projection, and this kind of projection is like mostly used, most of the maps that we use or default base maps are in Mercator projection. So this is a cylindrical projection, and here like your polar areas are like you see them large, but in actual real world it is not that large. Okay, so but like if you change the projection type, then the distortion type is going to change. Okay, so we can see this is the cylindrical one that we are seeing. Then we can also have a conical projection. So here like it will project as a cone. Okay, and then we also have planar projection. So planar projection are very good in representing the like polar areas, you can see. So uh, for planar area it is good. So now we'll see how these kind of maps look. So if you see a cylindrical or Mercator map, it will be like this. It is basically projecting like this. Okay, so the projection is going to be like this, and then in conical it will look something like this, and then we have planar and it will look something like this. Okay, so different projections are going to have different uh, like kind of distortions. So you need to understand what you are looking at, and you should always know which projection system we are using. Okay, so why same projection system is used? So because like in different projection you can see different locations are going to be at different places. So we need to have correct spatial alignment for analysis, so different projection can distort these positions. So now what I will do, I'll add a base map here and try to change the projection system. So let me add any map. So now if you see, can anybody tell which kind of projection it is? Just message in the chat box. What do you think? Which kind of projection is this? Answer? Cylindrical. Yes. Yes. So it is basically a cylindrical projection. So whenever you have a map, suppose you have a map, so what you can do, you can just go to the layer and right click on this and go to properties, and then you can go to source. So when you go to source, you can see this is pseudo Mercator. So Mercator was what? Cylindrical one, right? So this is a cylindrical projection. Now what we can do, we can change the reference system. So for changing, go to source, then go here in the assigned coordinate reference system, select CRS. CRS is coordinate reference system. So you can see there are like different kinds of projections. Um, Let me see. We can just play around different kinds of projections. So all are Mercator. So that is why I'm not using it. This is also cylindrical. What we'll do, I have to see which. So let me search. Maybe we can search plane. Let me apply this. No transform. So for each like base map, we need transform. Let me check. Plane. So now you can see this is kind of conical, but not exactly. Okay. So actually, I have to search like which projection type is defined how, because these are kind of predefined CRS. So we need to know the names. So I'll just search predefined CRS in conical projection. So this is Lambert something. So let us use this. Okay. So now if you see this, it is like conically represented, and it is the center is at which pole? South pole. Okay. So if you change different projections, so the main idea of like doing this is that if you change the projection system, then what will happen? Your uh, like your spatial alignment is going to change. Okay, so if you have aligned different projections in the same map, the same location is going to come at different places because of different projection types. Okay, so Lambert is for, let's see. So now the cones are at these points. Okay, so this is the kind of conical projection, and one we can look at planar one, right? So for planar projection, does anyone know? We define CRS. Let's see. Let us apply this and see. Okay, transformation is not available. So the main thing is like if you project in different projection system, what will happen? You will get like your alignment is going to be different. So that is why you need like uh, same projection for all the layers that you have uh, given. Okay. So, see. Now, if you see this, this is another kind of transformation. So, but the mostly used is Mercator type. So that is what we will be mostly using, this cylindrical type of Mercator projection. For planar, it
इसको
is orthographic. Sorry. Uh, any questions? Anyone? Okay. So no questions, then we can move forward. So the next question is, what is the difference between WGS 84 and UTM? So first option is WGS 84 is a projection and UTM is a datum. Second is WGS 84 is uh, a global datum and UTM is a projection system. And third one is only for India, WGS 84, and UTM is for Europe, and D is both are projections. Anyone? Which option? What is the difference between WGS 84 and UTM? No? Okay. So basically, WGS is a global datum and UTM means Universal Transverse Mercator. So Mercator is what? A projection system. Okay. So basically, the second option is correct. UTM is Universal Transverse Mercator. Okay. So this is a projection system. And WGS global datum basically means it is like a model that will like kind of uh, represent the 3D system in a 2D system. Okay, so this model or global datum is called as WGS 84. So there are different ways through which you can model it, model the Earth's shape, and WGS 84 is one of them. So, what are two major ethical and societal issues related to GIS? So, first is privacy and surveillance. So, if you are using geographic information system, so the issue is like you cannot use it for like privacy or surveillance issues, so you cannot track without like government's permission or something like that. And data ownership and access restrictions, so that are the two issues that are there in GIS. Now real world model. So this is one activity that you can do to understand what a real world model or GIS model is. So activity is to draw a map of your neighborhood from your memory, and you can label like where your house is as compared to house, where is your uh, park, where are the shops, where is the map, and then you can compare this with your the Google map. So the map that you are making from your memory is kind of a layer, JS layer, where you are making, like you are assigning some lines, vector lines to the roads, some polygons to the park or shops and house. So these are, like, this is basically what you have you in your memory, and then if you compare this with the Google map, this is going to be different. Okay, so the real world model and the digital world model are going to be, like, basically they can be different. And real world model, basically whatever model we have, they represent the human understanding of geographic phenomena in simplified models. So the real world is very complex, but when we are accessing it, trying to understand it, we kind of translate it such that, like, it is like simplified or we can understand it. Okay, so based on our understanding, we make these simplified data models of the real world. Okay, now what is data model? So data model is translation of the real world model into digital format, which is suitable for GIS and database. Okay, so if you are making a model of real world, so that model must be, like, suitable for GIS. So it can be either a raster data or a vector data. So these type of data sets should be there because the GIS is compatible with these type of data sets and databases. Okay. Now, what are the entities? So there can be different classification types like road, lakes. There can be different attributes. So each classification or uh, each property like road or lake is having to have some characteristic like area or depth, or for road it is going to be length, for lake it is going to be lake area. Then if you are talking about a country, then population can one of the attribute. So this, there can be this, and then there is relationship between these two, the type and the attribute. So relationship are basically mostly spatial or logical connections. So that means this belongs to, or this borders with, like, China borders with India, or um, borders on, so something like this. So there should be some relationship between the two uh, attributes or two types. Okay, so this is what relationship means. Now there can be different attribute types. So this is, like, you can just go through it and understand it. So basically, once you do that activity of drawing your neighborhood from the memory, you can miss a few lanes or shops. So what does this tell you? First is you are bad at remembering things. Second is maps are always better than memory. Third is mental map differs from actual data. And D is Google map is inaccurate. So what is that telling you? See, so mental map actually differ from uh, actual data. Okay, so every time, like, when we make some map GIS layer, that is kind of simplified version of what actually is there. Okay, so it is not like going to be 100% correct, but it is going to be a simplified version of what is there. Okay. Now, um, next is GIS model and object representation. So the different object types can be like roads, rivers, uh, these are some physical objects. Then there can be some classified like vegetation type. Then there can be continuous object type like rainfall, or some artificial like if you make the um, isohyets, which are lines of equal rainfall. So these are not actual lines that are there, but these are artificial lines. So these contours are artificial lines. So these are different object types that you can represent on in GIS. And now we have a question. So which of the following is a line entity in GIS? Tree, house, road, or pond? Okay, so everybody is right. It is road. Now, what is entity? So entity is a real world object or phenomenon that can be represented in GIS. So it can be a road, a tree, or a lake, something like this. Okay. So now the next question is water depth is equal to 15 meters. So what is this? An entity, a topology, an attribute, or a projection? Yes, correct. So this is an attribute. Attribute means it is defining, uh, defining, or it is kind of descriptive information about the data that we are talking about. So this is depth is the feature and it is 15 meters. So this is an attribute. Okay. So attribute is basically descriptive information about any entity. So tree height. So tree is entity, but height if you are going to tell, then it is an attribute. Lake depth. So lake is entity, but depth is attribute. Okay. So this descriptive information is called as attribute. Now the next question is, if a river passes through a village, the best GIS relationship term is containment, connectivity, adjacent, adjacency, sorry for this, adjacency, and then proximity. So which is like kind of telling you the relationship term. If a river passes through a village, what is that? So this is basically related to relationship term, connectivity. So connectivity is the correct term. So it is passing through the village. Okay. So it is kind of connected. So that is why it is connectivity. So a relationship is basically spatial or logical link between entities. So example is a river passes through a village. Okay. So now we have our next question. So we have three options. First is adjacent to, second is contained in, and third is intersect. So you have to connect the feature A, which is entity, feature A to feature B. So there are two entities, and we have to give spatial relationship between these two. School and city boundary, road A and river B, state park and national forest. So school is what to city boundary. Anybody? So school is contained in city boundary. Then road road A and river B. What they do? Mhm. Okay. Adjacent or could be intersect. Yeah, like both of them can be correct, but we also have this state park and national forest. So these two are going to intersect, and the other one, road A and river B is going to intersect, and state park and national forest are going to intersect, and these two are going to be adjacent. Okay, so this basically depends on how like you are uh, connecting a feature to to another feature. Okay, so these relationships are spatial relationships. Okay, now here you have to classify them either as attribute data or spatial data. So data item is latitude and longitude. What is this? Latitude and longitude of trees is spatial data or attribute data. You can write S for spatial, A for attribute. Yes. So anything that talks about the location or coordinate or address is going to be spatial data. And tree species, what is this? Spatial or attribute? Yes, it is attribute. Now, road network as lines. So, what is this? Road networks, spatial. Now, next one is average income per household. Yes, so this is going to be attribute. Next is elevation in DEM. What is this? So, maybe we can write this. This is spatial. This is attribute. This is spatial. Income is attribute. Now elevation is also attribute, and building height is also attribute. Yes. So now we know what is attribute, what is spatial data. It's very easy. Okay. Now, here also we have to classify them either as spatial or non-spatial. So calculating average population of district. This is spatial or not spatial? Yes, non-spatial. Now finding shortest route between two hospitals. So this shortest route is going to be spatial. Sorting villages by literacy rate is non-spatial, and finding overlap area between flood zone and settlement. This is spatial. Okay. Now, which feature should be represented as polygon in GIS? Electric pole, railway line, playground, or water tap? Yes, playground is the correct one. Okay, now object representation. We have zero dimensional point object like borehole or trees or cities. So these are going to be a point data. Line data is one dimensional like road, rivers, railway tracks. So these are going to be river network are going to be line. And polygon is two dimensional like lake area, not lake area, lake, city, city boundary, or if you want to represent a country or a state, then you will use a polygon. Okay. Now raster and vector we already know. Raster is grid based. Continuous data are going to be represented by raster, and vector is shape based like point, line and polygon all are vector data set. So discontinuous. So now you have to tell me satellite image is best represented as what? Vector, polygon, raster or attribute? Yes, so it is going to be a raster because mostly what we represent a continuous feature. We take image of the whole area and for each pixel we have one value. So this is kind of continuous data. So that can be represented by raster. Okay, so there are different data sources that we can use in GIS. So data sources can be either primary or secondary. So primary is basically when you go to a field and then you collect the data. Like suppose you go to a lake and then you collect the lake samples of water samples or snow samples. So whatever data you have is going to be primary. Or suppose your data is obtained from satellites, so remote sensing. So all are primary data sets where you are collecting the data. Okay, and then secondary data set is you are deriving the data from existing database or existing map or existing reports. So suppose somebody already reported that Delhi is having rainfall amount of this, or you are extracting, suppose there is a map and you are extracting the location of cities from that map. So this type of collection is secondary because you are using existing map or database or report for deriving the information. Okay, so there are these two data sets, primary and secondary. So there can be different sampling methods. So sampling method is what is the technique that you are using to collect the data points. So suppose if you use random, so there is equal chance for all locations. So this type of collection is kind of unbiased or scattered points. So randomly you have gone to a field and randomly you are taking data. So you don't have any pattern. When you have systematic sampling method, so suppose if I draw this, okay. So in random you will go like at any location and then you are going to collect. So every location is having equal probability of getting sampled, but it is going to be very random and scattered. So not very biased, okay. But if you are going for a systematic collection, then what you will do at every 1 kilometer or 5 kilometer, you are going to take one sample. Okay, so this will look like this. Sampling will be like this. So it should be like at each regular interval you are taking one data. Every kth point equal spacing, there is going to be equal spacing. And then stratified. So in stratified what we do, suppose this is your area of interest. Now what you are doing, you are you have like uh, different types of features, right? So like some lake area, some forest area, or like different classifications are there. And then you go and select samples from each of them, like each subpopulation, you are going to uh, get some data points so that each of the zones are kind of represented well. Okay, so this is kind of stratified uh, collection or sampling methods. So there here we do collection based on zones. Okay, and data types. can be different, like these road, river, framework, socio-economic like demographic, transport, housing, environmental like climate, population, or ecosystem. So this is not that important. Um, I'll move on to the next. So now you have to answer this question. If you collect, okay, already somebody answered, every 5 meters, so you can see there is like every kth or regular interval we are taking samples. So this is systematic. Now, should in flower, grass, zone, and then sample both. Which method is this? Systematic, stratified, random, or cluster? So you have a garden, and then, okay. So I think the stratified was not clear. So in stratified, what we do, you divide area into different zones. Suppose you have a garden, there is a flower zone and a grass zone. So you will sample both in flower zone and grass zone. Okay, so that particular method is called as stratified. So what you are doing, you are dividing your area into different zones, and then from each zone you are going to take some samples. So now is this clear? Stratified one. Now next question. A location is shown 500 meters away from where it actually is. What is the error? Attribute error, temporal error, logical error, positional. Yes, it is a positional error. Okay, so um, when we talk about object relationship, it can be derived from coordinates like its spatial location, like the spatial relationships that we were talking about. So it can be derived from coordinates like intersection and how it is related to a single point. Second is it can be derived from structure, so start and end of line, and attribute. So what is the information or value that we have for that location? Okay, so like if suppose there is some area which high digital elevation, okay, so that can be like high high elevation area, so that attribute is there. So this kind of relationship can be derived from these three. Now there are some data quality dimensions, so whatever data we have can have some errors also. So if there is a positional accuracy, uh, so for that we need to have correct geographic location. So whatever image that you have, your location of of the area that it is representing should be precise. So correct geographic location is positional accuracy. If there is correct data value, then it is attribute accuracy. Data validity over time means over the time if it is correct, then it is temporal accuracy. Then logical consistency means whatever uh, structure is there, there is consistency within it. And completeness, so if data is like complete, it is not like um, half representation. If it is half representation, that means that data quality is not good. And additional can be purpose uses lineage. Okay, so now we will talk about this positional accuracy, which is related to geographic location. Okay, so for that, um, we have different things like there can be different ways from which we can make a digitized maps. Okay, so what is digitization? Digitization is basically, suppose you have a map and you trace the map, you trace the map, then That tracing is called as digitization. Okay. So in manual we have physical maps and then we digitize, and in heads up digitization we trace on screen using scanned images. Okay, so this tracing or scanning is called as digitization. So this digitization can also be done in QGIS. So suppose you have a map and you want to extract the city locations or satellite or suppose you want to extract settlement locations from the map, then you can do digitization process. Okay, so we will be doing this process in today's class only, but before that, let's see what we have. Hmm. We are coming to the digitization and georeferencing thing only. Okay, so georeferencing and digitization, what is the difference? Georeferencing is process of aligning the real world coordinates to a raster image. So suppose you have a map or a satellite image and you want to align that with real world coordinates, then that is called as georeferencing. Okay. Now, what is digitizing? Digitizing is basically uh, a process of, like, you have a map, and what you are doing from the map, you are scanning the map and digitizing and converting it into a vector data by manually tracing it. Like you can generate data, a point shape file, line shape file, or a polygon shape file from these maps. Okay, so these two processes we are going to do in QGIS. So what I'll do, I'll take a 5 minute break and then we can start this digitization and georeferencing thing. Okay. So meanwhile, if you have any questions, you can ask or message in the chat box. Okay, and then we will start with the process of georeferencing and digitization. So yes, it is getting recorded, and the last time it got like the recording was like zoomed in, but now that issue is resolved. So this time you will get the full recording correctly. Okay, and I'll upload this. So I've told you where I'm going to upload and how can you access this. So you know how to go to this site, right? Okay, so if you missed it, actually, if you can go to this website, Swam portal, and you can see there is this problem solving session July 2026, and you can see here we have problem solving session recording, and if you click here, you will come to this link. So there is a presentation folder, so in which I have given you the PPT of the previous session. Okay, and I'll upload this session's PDF also, and there is this YouTube link that we have, but there was some problem with the last session, so it was kind of zoomed in. But right now it is recording correctly, so you will get full recording of this session. Okay, so and if you want to, yeah, I think you got it. So you just have to click here to get the problem solving session lectures. Okay, so anybody, anything else? Any questions? So no questions so far. So before doing the georeferencing step, I'll just tell you like what is the process that is happening when we are doing georeferencing. Okay, so let's see. First step of georeferencing is that you need to locate the ground control points, GCPs. So what is GCP? So GCP is basically, suppose this is your image and you have a topographic map of an area. So there are some features you can easily identify in both your image and your like topographic map. Okay, so those features can act as ground control points. So they are basically points which can be used to like give latitude and longitude values. Okay, so the points for which you know the exact latitude longitude values, or the point that you can align with your topographic map, is called as ground control point. So basically for a map you need minimum three ground control points to assign, and uh, like 4 is good, like for doing good transformation. So what happens when we give a ground control point? Suppose we gave 3 ground control point. So after assigning the ground control point, this will be kind of transformed to this image, and it will try to align such that the ground control points here and here are having minimum error. Okay, so they are kind of aligned with each other after transformation. So the source GCP and the transform GCP is going to have some error which is called as RMS error, and this RMS error should be less than the spatial resolution of the image. Okay, suppose the spatial resolution is 30 by 30 meters. So if the RMS error is more than 30 meters, then that control point is not good for transformation. Okay, so you should discard that ground control point. Okay, so this is what ground control points are for. And once you assign ground control point, then there is a transformation based on like what kind of equation you are using. So there can be linear or complex polynomial transformation. And after the transformation, what will happen? Your suppose your input image was like this. After transformation, your output image is like rotated slightly and like this. Now what happens? For each pixel we have some values, right? So if for each pixel we have some values, in the new image also we need to assign some values, right? So for assigning the values, you can do different resampling method. So the best one which we basically, or which is kind of default, is the nearest neighbor. Okay, so what it does, whatever is the nearest pixel to so suppose if we want to calculate for this particular pixel, the nearest pixel in the input image is getting assigned here. In bilinear interpolation, the 4 pixel which are nearest, average of that is will be assigned to the output image. In cubic convolution, you will add these 16 pixel values and then average it to assign the pixel at the center. Okay, so this is like different resampling method, and the best one is nearest neighbor because in the other ones you are kind of smoothing the image. Okay, but here the pixel values are kind of preserved. Okay, so this is what we do, and now uh, we'll go and do georeferencing in QGIS. So I'll not be able to do today in ArcGIS because I don't have ArcGIS in this laptop, but these are the steps. So I have written steps and also added images so that you can follow this and do georeferencing. And if you have any doubts, you can ask. And what I'll do, I'll just do georeferencing in QGIS. Okay. So first of all, what is the first step? We have to go to layer and go to georeferencer. So we'll go to, so this is QGIS interface. We'll go to layer and then you can see here we have georeferencer. We'll click on this and this tab will appear. Now what we will do? We have to add a raster image. So always for georeferencing, you need to add a raster image. So suppose if you have a map, so suppose if you have a map and you want to assign coordinates. So before this, what I'll do, I'll just add this just to show you why we are doing this. Mm, I'll just add that image because you saw that the coordinates were written. But why we are doing this? So now if you see, if I hover around this map, you can see the coordinates. They are not what is written on the map. So these are basically a JPG image or a PNG image where the coordinates are written. But when we try to align it with the actual reference system in this QGIS, then it is not happening. So for that we need to georeference this image. Okay. Now if I also add a uh, vector map which has references. So was India one of So I'm adding boundary of India. So now you can see the boundary is added, but it is not appearing here. If I zoom in, zoom into the layer, it is somewhere here. So you can see, so they are not aligned because this reference, it doesn't have any reference system right now. Okay. So you can see layer has no coordinate reference system set. The layer is not georeferenced as and has no geographic location available. So that is why we need to do georeferencing. Okay. So we'll go to layer, go to georeferencer. Now again add that map. Okay. So now in this map, what do we have? We have some locations that we know what is the actual lat long. Okay, so for this, it is 20° north and 160° east. Maybe this one, 80° north and So you should do as precise as you can, and you have to choose this at GCP point. So this is the ground control point that I was talking about. So we know this particular location is 80° north and what 160° east. So we can write 160° east and 80° north, and then okay. Now we have to add another. So if you see here, here we have GCP table. Okay, I'll add another location. So this is way minus 120° east and what 40° south. So minus 40. Now move on to the next point. 160° east and minus 40°. So now if you see, these 3 points are giving zero RMS error, zero residual. Okay. Now if we add another point, so what is this? Minus 120, and this is 80. So now you can see, like at least from 3 you can transform, but to get like the error you need at least 4 data points in the map. Okay, so once you have your ground control points and the residual errors are very small, then what you can do? You can go to this and start georeferencing. And suppose if your data points are not correct, some ground control point is giving a large error, so you can also use this to delete the ground control point. Okay, now I'll do start georeferencing. Now here you can see I was talking about transformation. So you can select any linear, polynomial, whatever transformation you want to do. And you can see we have these resampling methods which are nearest neighbor, bilinear, cubic. So you can choose nearest neighbor because it will not smoothen your image. Okay. So select OK. So I hope this is done. Suppose if, and now I have to add that particular. So that world map is now georeferenced, and we will add this. Okay. Let's see. Huh. So let's see. Okay. So the problem is it is showing invalid data source because we are adding this as a vector data set. So that is raster data set. So we need to add that as a raster data set. Okay. So once we add this, okay. So I think that was not georeference. We need to do it again. Okay. But this time what I will do, I'll use another map so that you can have like you can know different ways through which you can georeference. So if I add this map, you can see like we don't have any grids here. So no coordinate system is not written, grid is not there. So how can we georeference this? Any idea? Anyone? Any idea? We have these locations here: Delhi, Jaipur, Bhopal, Shillong. We know the latitude and longitude of these locations, right? So what we can do, we can just use these lat long to georeference this map. Okay, so ground control point, and this is Chandigarh. So can anyone tell what is the latitude and longitude of Chandigarh? So it is 76.78, and this is 30.73. Yes. Now we only have 1 point. Now we'll go for Bhubaneswar. So you should never select ground control points which are kind of linear. We should always select that is like from different sides, like all the four different sides. And it will be best if you use like uh, use like more than four ground control points, because what happens is that your like error is going to be reduced. Okay, so if you want more accuracy, then you need to go for more ground control points. Okay, so it was this 20.296. Now next can be Gandhinagar. So this is 72.648 and 23.2375. Okay, and now we'll go for another Bangalore. 59. Okay, so now you can see these RMS error or residuals are very small. So I we think like our ground control point is good. Now we have to set out file name, polynomial, nearest neighbor, modified. Okay, so we have to leave it for some time. Still not there. So all the steps that I have shown is here, you can see, and we also have these images, and it is like not very difficult. Okay, so you can just do like without anyone's help. Okay, so you can do this using QGIS and also ArcGIS if you want to do. Then you need to do these steps, follow these steps. So see, so suppose, so once you add a georeferenced map, then what will happen? It will kind of follow, like now you can see it is not giving this sign that this is not georeferenced, and now it is aligned with this shapefile which has coordinates. Okay, so now you can see these two are aligned. Also, like there is another way through which you can do it. So suppose if you go to layer and georeferencer, okay. So, you what you can do, you can also, like if there is a layer on the map that is that is already that already has a reference system, you can use that to align your map. Okay. So what I'll do, I'll just go to the georeferencer. Okay. And now if you choose this, this is uh, for moving the ground control. No, we don't need that. Let's see what this is doing. Okay, what this is doing. Um, hmm, I don't know why this is not working. So maybe I can tell that in the next class. Like there is a method. What you can do, select a point in this map, and then what you have to do, select the same location on the referenced point here. Okay, so from that what you can do, align the map that is not georeferenced with this one. Okay, so this way also you can do georeferencing. Okay, so right now we only have 7 minutes left. So what I can do is that we can like do these steps, this particular aligning externally on the layer map or our map, uh, that I can do in the next session. Meanwhile, what you can do, you can download QGIS and try to align any map using this georeferencing technique, and then what we'll do, I'll also use ArcGIS in the next class, so that like some users are using ArcGIS for these things, so I can tell you those steps also. And then what we will do, once the map is aligned, we will digitize the map and make a vector file out of it. Okay, so these steps will be done in the next session. Okay, so right now maybe, like, if you have any questions you can ask. Okay. So since we are out of time, um, we can do those steps in the next session. Okay. Anybody, any questions? So let's see. Any questions, anyone? If not, then we can end this session. Questions? So I'll recommend you downloading QGIS and see how you can do this georeferencing step on your own. And if you have any problems, you can ask. And also from the course, if you have any questions, you can ask. Okay. So, okay, then we'll end this session. So actually, that is taking some time right now, but it happens pretty fast. So maybe it is some issue with my OneDrive, maybe. So in the next session, we can go through this problem. Okay. So it was taking some time. I don't know why. Okay. So, okay. Thank you all. We can end this session now.